In this part of the lecture series of quantum mechanics, we'll discuss about probability and expectation values. Now, we'll all know about probability. Consider you have a coin. Okay. So the coin have a head on the top and say the tail at the bottom. Okay, you all know the coin. Now, consider you tossed the coin 5 times. Okay, how many times you tossed the coin? 5. So now consider that total number of toss is 5. 3 times you got an head. Okay, and 2 times you got a tail. Agreed? So what is the probability of getting in head? The probability of getting in head is high because you see in the 5 toss, out of 5, 3 tosses were head itself. Agreed? Now what is the probability of getting a tail in the next attempt? You see, out of 5 attempts, 5 is the total number of attempts, I got only 2 tails. Okay. So this is the concept of probability. So probability gives you an idea of what next event can you expect more. Now there's something called as expectation value. Expectation values itself says that you are expecting something. What are you expecting? So remember a cubical dice with numbers on it. Okay, 1, 2, 3, 4, 5, I guess up to 6. So this side you have 1, say this side you have 2, side you have 3. So in this way you have a dice. Now consider you have rolled the dice 6 times. So what is the total number of times you have rolled the dice? You have rolled it 6 times. Agreed. Now amazingly 5 times you got only 6 and only 1 time you got only 5. Agreed? So 5 times you got 6 and only 1 time you got 5. Now if I ask you what is the most expected number that you are actually getting by tossing this dice, then the most expected number, say n bar, the most expected number is, okay, so 5 times you got the 6, so 5 into 6 plus 1 time you got the 5, so 1 into 5 divided by what is the total number of attempts? Total number of attempts are 5 plus 1, that is 6. So what do you get here? You get a 35 divided by 6. So 35 divided by 6, if you do, you'll get approximately a 6. So you'll get 5 point something. So that will go near say 6. So what is the most expected value when you're tossing the dice? Of course it is a 6. So in this way you calculate the most expected value. Similarly, consider now a the expectation value. Now consider a diffraction experiment. Okay, so what we'll do is we'll calculate the expectation value only. So although diffraction experiment is a continuous thing, I mean the electron they uh, come continuously, but for a moment just assume things are discrete just for a moment. So consider there are positions with position x1, there are positions with position and x2, and there is another position x3. Similarly there is a position say x4, and this side I'm considering say the x-axis. Okay, now consider n1 number of electrons showed up x1 number of times. So n1 number of what? N1 number of electrons. Okay, so n1 number of electrons showed up at x1, n2 number of electrons showed up at x2, and so on. Okay, this happens say till n. Okay, now here I want to show a very interesting thing. If you look at this multiplication, look at 5 into 6, it can be done divided by 5 plus 1, 6. This 6 is this 5 plus 1. Agreed? And we have 1 divided by 6 into the number 5. So you can see that these are nothing but probability of getting a 6 multiplied with 6 plus this is the probability of getting a 5 multiplied with 5. Just remember this. Great. Now, so consider the Ni number of electrons showed up at position xi. Now, if I ask you what is the most expected value of position at which I can expect maximum number of electrons reaching. So how do you calculate? Same as the calculation you did in 2. So what you need to do is you just multiply number of electrons that showed up at x1, then multiply number of electrons n2 which showed up at x2, and dot 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 you did it till n. So number of electrons, that is Ni, showed up in position xi divided by total number of electrons. So you need to add n1, n2, n3 dot 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 till the Ni. Agreed? Now this calculation can be done, and this calculation can be written as what? Okay, I'm writing it in another color. Okay, so what is the lower part? The lower part is actually total number of electrons, that is summation Ni. So this is the total number of electrons. Now if you look at this particular mathematics that we did, okay, so if I just compare this with this, okay, then the new way of writing this will be, I guess, summation I probability at I multiplied with the position xi. Agreed? So it's very easy. Okay, so what is this that I'm actually calculating? I'm calculating the most expected position of x where I'll get maximum number of electrons. Now can you tell me what is the probability in case of quantum mechanics? In quantum mechanics the probability here was, so what I'll do is, instead of writing sum, okay, let me write things in a continuous manner, because if I write my probability like this, so remember what was my probability? So if I write my probability as psi squared dx, it means I am telling a probability, I am calculating the probability between x and x plus dx. So this brings in a continuity. So things are no longer discrete. So things are discrete here, but here things are no longer discrete, because the very if I write probability as psi squared dx, then it means I'm considering a continuous spectrum. So this will be psi square dx, that is the probability, and multiplication of this x, so this x will come here and there will be an integration. Agreed? So how do we write the expectation value? So let me write it here. So in quantum mechanics, expectation value is written as integration psi star, because psi square is what? Psi square is psi star psi. Keep the x in between and the other psi here into dx. This is the expectation value. Now the region where you are doing the expectation value, so this is 1D formula for expectation value. Okay, so if you are calculating the expectation value for the entire space of x-axis, then take it from minus infinity to infinity, or else it depends, the integration depends on your length of the x-axis. Agreed? So once you solve some problems, you will be very much clear of what this expectation value actually is. So I hope theoretically you understand how we write expectation value in quantum mechanics, and all these things have the origin from statistics. So I hope you got the main point, how things were discrete here and how things are continuous here. So if you look at this one, okay, if you look at this one, the moment I write my probability between x and x plus dx, things become continuous. So I made a jump from here to here, from discrete to continuous. So forgive me for that, but this is how it is. So I hope you got the if you look at this particular box, this box contains the value for expectation value in quantum mechanics. So you will be given the wave function. So after you are given the wave function, calculate the psi star of the wave function and then multiply x in between and then integrate to find the expectation value. Agreed? So in the next lecture, we'll explore more in quantum mechanics.